All right. The sort of underlying topic for today is really getting multi-core, getting good multi-core performance, getting good performance on multi-core hardware. And that's actually like a very interesting and deep, fascinating topic with many, many different interesting aspects. Today, we're just going to bite off a fairly small piece, and that's how to get good performance for shared data in the kernel that's read much more often than it's written. And it turns out there's many kind of specific cases in which different ideas for getting good multi-core performance are useful. And what we're going to look at today is Linux's RCU, which has been very successful for sort of read-heavy data, read-heavy kernel data. The general sort of background here is that if you have modern machines with 4 or 8 or 16 or 64 or however many cores running in parallel and sharing memory, the kernel is really a parallel process. It's a parallel program. And if you're going to get good performance, you need to make sure that the kernel can run a lot of its work as much as possible in parallel on different cores in order to get that much more. If you can run the kernel in parallel on 8 cores, all of them doing useful work, you can get 8 times the performance than if the kernel could only run on a single core. And at a high level, this should clearly be possible. If you have lots and lots of processes running on your computer, well, first of all, if the processes aren't running and executing in the kernel, then we have very little to worry about. They're likely to run in parallel without any kernel having to do anything. If the processes, if you have many applications running and they're all making system calls, a lot of the time, different system calls made by different processes just seem like they ought to be independent and should be able to proceed in many cases, though certainly not all, but should be able to proceed completely without interference. Like if 2 processes are forking, or 2 processes are reading different pipes, or reading or writing different files, there's no obvious reason why these should interfere with each other. Why they shouldn't be able to execute in parallel at n times the total throughput. But the problem is the kernel has a lot of shared resources. In order to, for other good reasons, the kernel shares a lot of resources like memory and CPUs and a disk cache and an inode cache and all this other stuff that's actually under the hood shared between different processes. And that means that even if 2 processors are doing system calls, 2 processes that have totally never heard of each other and aren't trying to interact, make system calls, if those system calls happen to allocate memory or use the disk cache, or involve scheduling decisions, they may well end up both using data structures in the kernel, and therefore we need some story for how they're both supposed to use the same data without getting underfoot, without interfering with each other. And there's been enormous effort over the years in making kernels, in making all these cases in kernels run fast. We've seen one, of course, that's oriented towards correctness, namely spin locks. Spin locks are straightforward as such things go and easy to reason about. But what a spin lock does is prevent execution. Its job is to prevent parallelism in cases where there might be a problem between 2 processes. And so spin locks are just directly a way to decrease performance. That's all they do. Of course, they make it easy to reason about correctness, but they absolutely prevent parallel execution. And that's not always that desirable. Okay, so again, we're going to focus on read-heavy data, on the case in which you have data that's mostly read and relatively rarely written. And the main example I'm going to use is a linked list, a singly linked list. And so you can think of just the standard linked list diagram. There's some sort of maybe global variable that's a pointer, this head pointer. It's just a pointer, and there's a bunch of list elements. And each list element has some data in it. And we'll just say it's a string, like, hello is the sort of data in this element. And each element also has a next pointer that points to the next list element. And then finally, there's a pointer that points to 0 to mark the end. So very straightforward. And again, we're going to assume that most uses of this list that we're interested in are just reads. The kernel thread or whatever it is that's using this list is just scanning the list looking for something. It's not trying to modify the list. And occasional writers, though, if there were 0 writers ever, we wouldn't need to have to worry about this at all, because it'd be a completely static list, never changes. We can read it freely. But we're going to imagine that every once in a while somebody comes along and wants to write the list. So that may mean that some other thread wants to change the data stored in a list element, or maybe delete an element, or maybe insert a new element somewhere. So even though we're aiming at mostly reads, we do have to worry about writes. We need to make the reads safe in the face of writes. And of course, in XV6, we just have a lock protecting this list and a reader. Not only would writers in XV6, not only would writers have to acquire the lock, but readers would have to acquire the lock too, because we got to rule out the situation in which, while we're reading, somebody's actually modifying the list, because that could cause sort of the reader to see a half updated value or follow an invalid pointer or something. So in XV6, we'd have locks. But that has a defect that if the common case is there's no writers, it means that every time somebody comes along and reads, in XV6, they grab an exclusive, like XV6 spin locks are exclusive. Even if you have just 2 readers, only one of them can proceed at a time. So what we'd like, or sort of one way to improve this situation, would be to have a new kind of lock that allows multiple readers, but only one writer. And so I'm going to explore those next, actually, both because they're interesting and because they help motivate the need for RCU, which we'll talk about in a little while. So there's this notion called read-write locks. And the interface is a little more complicated than the spin locks we're used to. We're going to imagine that there's one set of call that you call if you just want to read something. So we're going to imagine an rlock call. You pass it a lock, and then also an runlock call. And readers call these, and then there's a write lock call and a write unlock call also. And the semantics are that you can either have multiple readers acquire the lock for reading, so we would get parallelism, or you can have exactly one writer have acquired the lock, but you can never have a mix. You can never be in the locks rule out the read-write locks rule out the possibility of somebody having the lock for writing and also reading at the same time. You either get one writer or lots of readers, but nothing else. So that's the
question.
Yes.
This may be an implementation detail, but what kind of mechanisms does this locking scheme put in place to prevent someone writing while they hold a read lock?
Nothing. It's just like XV6 locks. They're completely, we're talking about kernel code written by trusted, responsible developers. And so just like spin locks in XV6, if the code that's using the lock's incorrect, it's incorrect. There's no...
Okay.
And this is the way, typical kernels are written. You just have to assume that people developing the kernel are following their own rules. Okay, and again, the reason why we care is that if we have a read mostly data structure, we'd love to have multiple readers be able to use it at the same time to get genuine speed up from having multiple cores. All right, so if there were no problem here, this would just be the answer, and we wouldn't have needed to read today's paper. But it turns out that if you dig into the details of what actually happens when you use read-write locks, especially for data that's actually read a lot, there's some problems. And in order to see what's going on, we actually have to look at the implementation. Linux indeed has read-write lock implementation in it, and this is a kind of simplified version of the Linux code. The idea is that we have a struct RW lock, which is like struct lock in xv6, and it has a count in it. If the count is 0, that means that the lock is not held by anybody in any form. If the count is -1, that means that a writer has it locked. And if the count is greater than 0, that means that n readers have it locked. And we need to keep track of them because we can only let a writer in if the number of readers descends to 0. Okay, so somebody asked about adding. No, I'm not sure if there's a question in the chat. Interrupt me if there is. The read lock function, it has to sit in a loop because if there's a writer, we have to wait for the writer. It looks, it grabs a copy of the current n value. If it's less than 0, that means there's a writer, and we just need to continue our loop and we're going to spin, waiting for the writer to go away. Otherwise, we want to increment that value. But we only want to increment it if it's still greater than or equal to 0. So we can't, there's many things we can't do. We can't, for example, just add 1 with standard n equals n plus 1. Because if a writer sneaks in between when we check the value of n and when we actually try to increment it, then we may actually go ahead and increment it at the same time that some writer is setting it to -1, which is wrong. So we need to increment it only if it hasn't changed value since we checked it and verified that it's greater than or equal to 0. And the way people do that is they take advantage of special atomic or interlocked instructions, which we saw before for the for our implementation of spin locks in xv6. And the interlocked instruction that's one that's particularly convenient to use is something called compare and swap. And the idea is that compare and swap takes 3 arguments: the address of some location of memory that we want to act on, the value that we think it holds, and the value that we'd like it to hold. And the semantics of compare and swap are that the hardware checks. The hardware first sort of basically sets an internal lock that makes only one compare and swap execute at a time on a given memory location. Then the hardware checks that the current value of that location is indeed still x. And if it's still x, sets it to this third argument, which is going to be x plus 1. And then the instruction yields 1 as its value. If compare and swap observes that the current value isn't x, then it doesn't change the value, the memory location, and it returns 0. So this is basically an atomic, if the location is x, set it to x plus 1. And it has to be atomic because there's really 2 things going on. The hardware is checking the current value and setting it to a new value. Any questions about compare and swap?
I have a question. If there would be a reader and our lock needs to continue, would W unlock reset the value back to X?
Oh, well, W unlock, if there's a writer, W unlock, which I'm afraid I didn't show, sets n to 0 because there can only be one writer. If there's, what read unlock does is use another compare and swap to decrement n.
Okay, because what happens if a writer locks the lock between when X is being computed and
Say right here.
no, between the if and X somehow.
Okay, I'm not sure I understand exactly what time you're asking, but it's absolutely a good question. What happens if W lock is called somewhere during this sequence? And for me, the most dangerous time for wlock to be called is after this check, but before the compare and swap. So let's imagine that readlock has gotten as far as seeing that x or LRON is 0. Okay, so maybe we're right here, and x is equal to 0. And we've already checked it. So the check is finished. And then right at this time on another core, some other thread calls wlock. And it actually gets its compare and swap in first. So on the other core that's trying to grab the right lock, compare and swap is going to see if LRON is 0. And let's assume that n is 0, so that this test is true, and the compare and swap is on that other core is going to set n to -1. So now the lock's locked, but we still think that n is 0 in this code, even though the lock's locked. And now we're going to execute, now back on the reading core, we're going to execute compare and swap, but we're going to pass 0 here, right? This is the value we're going to pass in the value we actually looked at, not the current value of n. And when we looked at it, it was 0. So we're going to pass 0 here. And we're telling compare and swap, look, only add 1 to it, only set it to 1 if its current value is 0. But it's not 0 at this point, it's -1. And so this compare and swap fails, does not modify n, returns 0. And so that means we'll go back to the top of this loop and try again. Of course, now n is -1.
This might be related to the previous question a bit, but is it possible for an interrupt to occur when that x+1 is being computed in the CAS parameter or CAS parameter?
You mean before we actually execute CAS, but while we're computing its arguments?
Right. So like you compute or you pass in the x argument, and that's okay. But before you compute the x+1 or while you're computing x+1, an interrupt occurs.
Okay.
And so x+1 is wrong.
So if an interrupt occurs while we're computing x+1, that means we haven't, CAS is actually an instruction. It's a single machine instruction. So if we're computing x+1, that means we haven't called CAS yet. If the interrupt happens, and all kinds of things may happen, we're going to get the same, if we originally read 0 here, right, then interrupt or no interrupt, we're going to pass 1 as this third argument, because the interrupt's not going to reach out and change. This x is a local variable for this code. So interrupt or context switch or anything is not going to change x. And so that means we're going to pass 0 and 1 here. And if n is still 0, then we'll set it to 1, and that's what we want. If it's not still 0, then compare and swap won't change it.
Right. I guess you would have problems if you didn't set that local variable then.
Yeah, if you used LRON here,
yeah,
and LRON +1, you would almost certainly be in big trouble, because then n could change underfoot at any time. That's why we actually grab a copy here in order to sort of fix a specific value.
Yeah.
Yes. Okay. If two readers, okay, so I covered the case of whatever writer calls at the same, whatever wlock is called at the same time as rlock. It's also interesting to wonder what if rlock is called at the same time. So supposing n starts out as 0, we know if two rlocks are called at the same time, what we want is for n to end up with value 2 and for both rlocks to return. That's what we want, because we want two readers to be able to execute in parallel, to use the data in parallel. Okay, so they're both going to see 0 at this point. So at this point, both of them are going to have x equal to 0. They're both going to call compare and swap with 0 and 1. Only one of those two compare and swaps, hopefully exactly one of those two compare and swaps will succeed. Whichever one, compare and swap is an atomic instruction. Only one of them happens at a time on a given memory location. So whichever compare and swap is first, we'll see that n is equal to 0, and we'll set it to 1. The other core's simultaneous call to rlock, its compare and swap will then execute, and it'll still pass 0 and 1 here. But n will now be equal to 1, and so the compare and swap will fail of the second core and return 0. The second core will go back to the top of this loop. At this point, it'll read 1. That's not less than 0, so we'll go on to the compare and swap, and now it'll pass 1 and 2, and now the second read lock will succeed. Both of them will have the lock. So the first one succeeded in the first try, the second one actually go back to the loop and try again. Any questions?
Oh, sorry. So it is somehow possible that, so a bunch of reads come and they're reading their stuff, and then a write also comes and it also wants to write, but then some other reads also come after the write, but then
Okay.
somehow the reads like outrun the write, and the write still has to wait somehow.
Yeah.
Or-
So if the sequence is that a reader managed to acquire the lock, one or more readers have the lock. So now n, each of them, this is called a compare and swap, adds 1 to n for each reader. So now n is greater than 0 because there's multiple readers. If a writer tries to acquire the lock at this point, the writers compare and swap, the compare value is 0. So compare and swap will only change n to -1 if its current value is 0. But we know the current, because there's multiple readers, the current value of n is not 0, and so the compare and swap will fail and return 0, and the writer will sit here in this loop, basically waiting until n is equal to 0 before its compare and swap will succeed and return and give the lock to the writer. So this certainly means the writer can be starved. If there's a lot of readers, n may never be 0, and so the write may never succeed. So that's a defect in this locking scheme.
Thank you.
I also have a question about the 2 readers scenario that I just mentioned. It appears that in the worst case, the reader that arrives second has to go through another iteration of the loop.
Oh, yes.
Which sounds somewhat wasteful.
You
And I
got
wonder if this generalizes to n writers.
It certainly does.
They all have to get lost and
And
start again.
You have put your finger on why people don't like this scheme. If there's a lot of simultaneous reader. And so for the reason you just mentioned, RLock, even if there's no writers at all, if there's lots of readers or there's readers on many cores, RLock can be very, very expensive. And one thing you need to know about the RLock scheme, which I think we've already mentioned in class, is that on a multi-core system, every core has an associated cache. We'll say it's the L1 cache. So each core has a bit of cache memory. And whenever it reads or writes something, it sits in the cache. And so there may be lots and lots of cores, and there's some kind of interconnect network that allows the cores to talk to each other. Because, of course, if lots of cores have some data cached, and one of the cores writes that data, the writing core has to tell the other cores that they're not allowed to cache the data anymore, which is called invalidation. So what actually happens if you have n readers, n people calling RLock at about the same time on n cores, they're all going to read this L arrow n value and load this memory location into their caches. They're all going to call compare and swap. The first one to actually call compare and swap is going to modify the data, but in order for it to modify the data, it has to invalidate all these other copies. And so the compare and swap instruction that 1 has to send out an invalidate message over this little network to each of the other n cores, right? And then it returns all the other cores, the n-1 cores. They have their compare and swaps now actually have to reread, again requiring traffic over the network, reread this data, this memory location, compare it with x, and they'll have failed because they all call x with 0. Then the remaining n-1 readers go back to the top of the loop, and all n-1 of them again read the data, and again one of them writes it. Right. So on each So there's going to be n times through the loop, once for each core trying to acquire the lock. Each of those trips through the loop involves order n messages on the network, because at least every copy of the cached LRON has to be invalidated. And that means that the total cost for n cores to acquire a particular lock, even for reading, is order n. And that means as you increase the number of cores for a popular piece of data, the cost for everybody to lock it just once goes up. Sorry, it's order n squared. The total cost in time or messages sent over this interconnect is n squared. And this is a very bad deal, right? You would hope that if you needed to do something 10 times, 10 different cores needed to do something, especially, given that they're just reading the list, they're not modifying it, you'd hope that they could really run in parallel. That is, the total wall clock time for 16 cores to read something should be the same as the total wall clock time for 1 core to read something, because that's what getting parallelism means, is that you can do things at the same time. But here, the more cores that try to read this, the more expensive the lock acquisition is. And so what's going on is that this style of locks has converted read-only access to data. The list is probably sitting in the cache already because nobody's modifying the list, right? So the actual access to the list might only take a few dozen cycles. But if the data is popular, getting the lock can take hundreds or thousands of cycles because of this n squared effect. And the fact that instead of it being cached accesses, it's these accesses that have to go over the bus, this interconnect, in order to invalidate and do these cache coherence operations. So these locks have turned a very cheap read-only access to data into an extremely expensive read-write access to this data, right? And will probably completely destroy any possible parallel performance if what you were doing, if the actual data was fairly simple to read, the lock will dominate and destroy parallel performance. So any questions about this performance story? In a sense, the bad performance of read-write locks is the reason for the existence of RCU. Because if this was efficient, then there'll be no need to do better than that, right? But it's terribly inefficient. And there's two things going on. One is the details of this. Oh, there needs to be a total of n squared trips through this loop if we have n cores, is sort of one way of looking at it. The other way of looking at it is that we're writing, regardless of the details of what's going on here, these locks have turned a read-only access, which could be cached and extremely fast, into an access that one way or another involves a write, one or more writes. And writes are just much more expensive than reads if we're writing data that might be shared with other cores. Because a read for data that's not modified can be satisfied in a couple cycles out of your own cache. Any write to data that may be cached by other cores has to involve communication between cores to invalidate other copies. So no matter how you slice it, anything that involves a write to shared data is a disaster for performance if you otherwise could have been read-only. So the details of this loop are sort of less important than the fact that it did a write to shared data. So what we're looking for is a way to be able to read data without writes, right? We want to be able to scan that list without doing any writes whatsoever, including any writes that might be required to do some kind of locking thing. So we're looking for really, really read-only access to data. Okay. So one possibility, it's not a possibility, but it's sort of a thought experiment, is we could just have the readers not bother locking, right? Occasionally you get lucky and it turns out that readers can read stuff and that only writers need to lock. So we'll just do a quick experiment to see whether we could have lock, just have readers just read the list without locking it. So suppose we have this list and it has some, strings. And we're going to read it. Okay, so nothing goes wrong if there's no writer, right? You just read the list. It's not a problem. So we got to imagine there's a writer. And there's probably 3 cases if you read a list while some other core is modifying it. So one case is that the writer is just changing the content. That is, not adding or deleting elements necessarily. A writer is just changing the string to be some other string. So one is the writer is changing the content. 2 is the writer is inserting a new list element. And the third case is if the writer is deleting a list element. And I want to examine these because we need a story for each, and RCU actually kind of has a story for each. So the danger, so I'm just talking about what goes wrong if somebody's reading a list while another core is writing it. If the writer wants to, it just changes this string, then the danger is that the reader will be actually reading the bytes of this string or whatever else is in the list element while the writer is modifying the same bytes. And so if we don't do anything special, the reader will see some mixture of the old bytes and the new bytes. And that's probably a disaster. So that's one case we have to worry about. Another possibility is that the writer is inserting a new element. And of course, what that means is that, supposing the writer wants to insert the new element at the head, the writer's going to cook up some new element, going to change the head pointer to point to it, and going to change the new element to point at the old first element, right? And so the danger here, if a reader is reading the list while the writer is inserting, is that maybe, if we really blow it, the writer may set the head pointer to point to the new element before the new element's initialized. That is, while it maybe contains garbage for the string or some illegal pointer as the next element. So that's the thing that could go wrong if a writer's inserting. So let's, and if the writer's deleting, then what it means to delete an element is first to change, let's say we're deleting the first element, we change the head pointer to point to the second element, and then call free on the first element to return this to the free list. And the danger here, if the reader sees the new head pointer, that's fine. They're just going to go on to the second element instead of the first. If the reader actually was looking at the first element and then the writer freed it, then the problem we have is now the reader is looking at an element that's on the free list and could be allocated for some other use and overwritten for some completely other use while the reader's still looking at this element. And so from the reader point of view now, all of a sudden the element's filled with garbage instead it was expecting. So that's the third case we have to, if we want to have lock, if we want to have absolutely no locks for readers, we have to worry about these 3 situations. And I'm not talking about writer versus writer problems here, because I'm just assuming for this entire lecture that writers still use locks, that there's still some ordinary like XV6 style spin lock here, and writers acquire this lock before doing anything, but readers don't acquire any lock whatsoever. Questions about these dangers? Okay. The point is we can't just simply have readers read with no locks, but it turns out we can fix these specific problems. And that takes us to RCU. And RCU has a couple of ideas in it that RCU is, by the way, it's as much a kind of approach to concurrency, concurrency control as it is a particular algorithm, right? It's a way of structuring, it's an approach to structuring readers and writers so that they can get along with the readers not having to take locks. The general game with read, copy, update is we're going to fix those 3 situations in which readers might get into trouble if there's concurrent writers, and we're going to do it by making the writers a little bit more complicated. So the writer is going to end up somewhat slower. They still need to lock plus follow some extra rules, but the reward will be the readers will be dramatically faster because they can operate without locks and without ever writing memory. Okay, so the first big idea in RCU is that in the first trouble situation we talked about before, where the writer is updating a list element, the content of a list element, we're going to actually outlaw that. We're going to say writers are not allowed to modify the contents of list elements. Instead, if we have a linked list like this with a couple of elements, if a writer wanted to update the content of element 2, instead of changing it in place, which it wouldn't do, it would actually cook up, it would call the allocator to allocate a new element. It would initialize the element completely. So whatever new content, we wanted to put here instead of the old content, the writer would set the next pointer on this new element so that this new element is now completely correct looking. And then in a single write to E1's next pointer, the writer would switch E1 from pointing to the old version of E2 to pointing to the new version of E2. So the game is, instead of updating things in place, we're going to replace them with new versions of the same data. And so, so now a reader, if a reader's gotten as far as E1 and is just looking at E1's next pointer, the reader's going to either see the old next pointer, which points to E2, and that's fine because nobody was changing E2, or the reader's going to see the new next pointer and look at the new list element. And either way, since the writer fully initialized this list element before setting E1's next pointer, either way, the reader's going to see a correct next pointer that points to E3. So the point is the reader will never see a string that's in the process of being, a content that's in the process of being modified. Any questions about this particular idea?
What about freeing?
Sorry.
Okay, I can go ahead. Will the link between E2 and E3 be deleted, or will it be left there in case that a reader somehow reached E2?
For now, we're just going to leave it. I'll come to this. This is an excellent question. And it's actually the main piece of complexity in RCU. But for now, we're just going to imagine that E2 is left alone for the moment.
The link from E2 to E3, we don't need to worry about it anyway, right? Because that's a part of E2, and like in normal implementations, we just free that anyway. Like with no RCU involved, we don't ever need to worry about that link, right?
Well, the danger is that just before we changed this next pointer, that some reader had followed the next pointer to E2. Right. So what we're worried about here is that some reader on some course is actually right now reading E2. So we'd better not free it right away.
Right.
So that's all, I think that's all we're saying is you better not free E2 right away. Just leave it alone. As a piece of jargon, the swap of E1's next pointer from the old E2 to the new E2, in my head, I call this a committing write. There's and part of the reason why this works is that with a single committing write, which is atomic, like writes to pointers on the machines we use are atomic in the sense that either the write to the pointer happened or didn't happen from the perspective of readers. Because they're atomic, basically with that one instruction, with the one atomic store, we can, it's an ordinary store, but it's indivisible. We switch E1 from pointing to the next pointer from pointing to the old one to the new one. And that write is what sort of commits us to now using the second version. This is a very basic technique, a very important technique for RCU. And What it means is that RCU is really mostly applicable to data structures for which you can have single committing writes. So that means there's some data structures which are quite awkward in the scheme, like a doubly linked list, where every element is pointed to from two different pointers. Now we can't get rid of list elements with a single committing write because there's two pointers to it. We can't, on most machines, you can't atomically change two different memory locations at the same time. So doubly linked lists are not so good for RCU. A data structure that is good is a tree, right? If you have a tree of a tree of nodes like this, then we can do, supposing we want to change, we want to modify this value down here. What we can do, there's some head to the tree. What we can do is cook up a new version of this part of the tree here, and with a single committing write to the head pointer, switch to the new version of the tree. And so the new version of the tree, which will, the writer will allocate, would sort of create, can actually share, for convenience, can share structure, the unmodified part with the old tree, and then with a single committing write, we're going to change the head pointer to the tree head pointer to point to the new version. But for other data structures that don't look like lister trees, it's not so easy to use RCU. Okay, so that's the first idea. Any last questions? The second idea one of the problems with one of the potential problems with the scheme I just described, we're going to cook up a new E2 prime, and what I said was, oh well, we'll initialize the content for E2 prime, and we'll set its next pointer correctly, and after that we'll set E1's next pointer to point to E2. As you may recall from discussions of XV6, by default there's no after that on these machines. The compiler and the hardware, basically all compilers and many microprocessors, reorder memory operations. So if you simply, say we allocate a new element and we just wrote this C code, E arrow next equals, E3, and then E1 arrow next equals E. This is not going to work well. This is not going to work reliably. It's going to work fine when you test it, but it won't work in real life all the time. Occasionally it'll go wrong. And the reason is that the compiler may end up reordering these writes, or the machine may end up reordering these writes, or the reading code which reads these various things, the compiler or the machine, the microprocessor, may end up reordering the reader's reads. And of course, if we set E1 arrow next to point to E2 before we initialize the content of E2, so that its string it holds or its next pointer point off into space, then some reader is going to see this pointer, follow it, read garbage, and crash. So the second idea is that both readers and writers have to use memory barriers. Even though we're not locking, or really because we're not locking, the writers and the readers have to use a barrier. And for writers, the place the barrier has to go is before the committing write. So we need a barrier here that tells the hardware and the compiler, look, all the writes before this barrier, please finish them before doing any writes after the barrier, so that E2 is fully initialized before we set E1 to point to it. And on the read side, the reader needs to load E1 arrow next into some temporary location or register. So we'll just say, register 1 equals E1 arrow next. Then the reader needs a barrier. And then the reader is going to look at R1 arrow its content and R1 arrow next. And what this barrier on the reader says is, don't issue any of these loads until after we've completed this load. So the reader is going to look at E1 arrow next and either get the old E2 or the new E2. And then the barrier says that only then are we going to start looking at, only after we've grabbed this, all these reads have to execute after this read. And since the writer guaranteed to initialize the content before committing the pointer to the new E2, that means these reads, if this pointer points to the new E2, that means these reads are guaranteed to see the initialized content. Okay. So we saw a little bit of this.
Sorry, but how can you? I'm sorry. Oh yeah, I was confused about the reader. So how can you read R1 like anything before you read R1? I guess how would they? So yeah, I guess like even if it reordered it, how would it be able to read R1X before it read E1 next?
I think you've stumped me. Yeah, I mean, what you're pointing out is that before you even know what the pointer is, you can't possibly actually issue the reads. A possibility is that whatever this pointer points to maybe is already cached on this core due to some, maybe, this memory had been, a minute ago used for something else, something totally else. And we have an old version of this cached on our core at this address, but for some previous use of the memory. If this read was to use the old cached value, I'm not sure this can happen. I'm just making this up for you. But if this read could use the old cached value, then we'd be in big trouble. And I don't know if the machine would actually do that, or whether another possibility is that the compiler, the real answer is I don't know. I should go off and think about what a specific example would be.
Okay, I see the cached version makes some sense. Yes.
Yeah, I'm not actually completely sure it could happen in real life. That's a good question. Okay. So that's the second idea. The third problem we have, which is something somebody raised before, is that the writer is going to swap the E1 pointer to point to the new E2, but there could be readers, who started looking at, who followed this pointer just before the writer changed it, who are still looking at E2. We need to free this list element someday. But we better not free it while some reader is still using it. So we need to somehow wait until the last reader has finished using E2 before we can free it. And that's the sort of third and final main problem that RCU solves, is how long should the writer wait before it frees E2? You could imagine a number of ways of doing this. For example, we could put a little reference count in every list element and have readers increment it and have writers wait. Readers increment it when they start using a list element, decrement it when they're done using the list element, and have the writer wait for the reference count on this element to go to 0. We would regret that instantly, because the whole point of RCU is to allow reading without writing, because we know that if lots of readers are changing this reference count, it's going to be terribly expensive to do the writes involved in maintaining a reference count. So we absolutely don't want reference counts. Another possibility would be use a garbage collected language. And in the garbage collected language, you don't ever free anything explicitly. Instead, the garbage collector does the bookkeeping required to decide if any thread, for example, or any data structure still has a reference to this element. And the garbage collector, once it proves this element can't possibly be ever used again, only then will the garbage collector free this. So that's another quite possibly reasonable scheme for deciding when to free this list element. You know, Linux, which uses RCU, is not written in a garbage collected language. So, and we're not even sure the garbage collection would improve performance. So we can't use a standard garbage collector here. And instead, RCU uses another sort of a trick that works well in the kernel for delaying freeze. And so that idea is that readers and writers have to each follow a rule that will allow writers to delay the freeze. Readers are not allowed to hold a pointer to RCU protected data across a context switch. So a reader is not allowed to hold a pointer to one of those list elements across a context switch. So the readers, they cannot yield the CPU in a RCU critical section. And then what the writers do is they delay the free until every core has context switched at least once. So this is easy enough. Like this is actually also a rule for spin locks. In a spin lock critical section, you can't yield the CPU. But nevertheless, you do have to be a bit careful. This is a little more involved, but it's relatively clear when each core knows it's context switching. And so this is a pretty well-defined point for the writer to have to wait for. And just requires some implementation. This also requires, this may be a significant delay. It may be a millisecond or a significant fraction of a millisecond that the writer has to wait before it's allowed to free that list element to be sure that no reader could possibly still be using it. People have come up with a bunch of techniques for actually implementing this wait. The straightforward one the paper talks about is that the writing thread simply arranges with the scheduler to have the writing thread be executed briefly on every one of the cores in the system. And what that means is that every one of the cores must have done a context switch during this process. And since readers can't hold stuff across context switches, that means that the writer has now waited long enough. And so the way the actual writer code looks like is the writing code does whatever modifications it's going to do to the data, and then it calls this synchronize RCU call, which actually implements 2. And then the writer frees whatever the old element was. And so that means that the writer is doing whatever it's doing. At this point, let's say it's doing the E1 arrow next is equal to the new list element. And so this synchronized RCU forces a context switch on every core. So any core that could have read, the old value must have read it at this point. Must have read it at this point in time. If after that point in time we've done a context switch on every core, that means that no core that read the old value could still have a pointer to that value at this point in time due to rule 1. And that means that we're allowed to free the old value. Any questions? You may object that this synchronized RCU will take a significant, perhaps fraction of a millisecond. That's quite true. So that's too bad. One of the justifications is that writing, for RCU protected data, writing is going to be relatively rare. So the fact that the writes take longer may not, probably not affect overall performance very much. For the situations in which the writer really doesn't want to wait, there's another call that defers even the wait, called call RCU. And the idea is you pass it in the usual use case, you pass it a pointer to the object you want to free, and then a callback function that just calls free on this pointer. And the RCU system basically stashes away, the call RCU stashes away these two values on a list and then immediately returns. And then does some bookkeeping, typically involving basically looking at the counts of how many context switches have occurred on each core. The system sort of in the background after call RCU returns does some bookkeeping to wait until all cores have context switch and then calls this callback function with this argument. And so this is a way of avoiding the wait because this call returns instantly. On the other hand, you're discouraged from using it because now this list that if the kernel calls call RCU a lot, then the list that holds these values can get very long, and it means that there may be a lot of memory that's not being freed. This list grows very long. Each list element has a pointer in it that should be freed, a pointer to an object that should be freed. And so under extreme circumstances, you can run a system out of, if you're not careful, a lot of calls to RCU, call RCU can run a system out of memory because all the memory ends up on this list of deferred frees. So people don't like to use this if they don't have to. Okay. Please ask questions if you have questions.
So this doesn't, this prevents us from freeing something that somebody's still using.
Yes.
But it doesn't prevent us from having the reader see a half-baked version of something because it's being modified, right?
Idea 1 prevented that, yeah.
Okay.
So the idea behind idea 1 is that instead of updating a list element in place, which would absolutely cause the problem you mentioned, when writers are not allowed to update RCU protected data in place, instead they cook up a new data element and sort of swap it into the data structure with a single committing write.
Oh, and the swap in will be atomic, so there's no problem of
right.
Okay.
Because that's a single pointer write, which is atomic, whereas overwriting a string is completely not atomic.
That makes sense.
Other questions?
Does condition 1 in idea 3 mean we need to be careful about how much work we put inside those protected sections, since it kind of hogs the core for that entire section?
Yes. So this is that's right. So readers in the sort of RCU critical section, while they're looking at the protected data, they can't context switch, and so you want to keep those critical sections short. Now, and that's a consideration. The way it plays out, though, is that the way RCU has been deployed is typically that there'll be some piece of code in Linux that was protected with ordinary locks or read-write locks. And somebody, for some workloads, will see, oh, that lock is a terrible performance problem, and they're going to replace the locking critical section with an RCU critical section, although sometimes it's more involved than that. And since locking critical sections it was extremely important to make them short, because while you hold a lock, there may be lots of other cores waiting for that lock. So there was a lot of pressure to keep ordinary lock critical sections short. Because RCU critical sections are often sort of revised lock critical sections, things that used to be lock critical sections, they tend to be short also. And that means that not always, but usually there's not a direct worry about keeping the RCU critical section short, although it is a constraint. The real constraint actually is you're not allowed to hold pointers over pointers to RCU data over context switches. And that's actually you can't, for example, read the disk and wait for the disk read to complete while holding on onto a pointer to RCU protected data. So it's not quite so much the thing that usually comes up is not the length of the critical section so much as the prohibition against yielding CPU. Okay. Let's see. So just to kind of firm up all the stuff I just talked about, here's a kind of what you would see in a simple use of RCU. So this is code you might see for reading a list, an RCU protected list. And this is the code you might see on the right side for code that just wants to, the particular case of replacing the first list element. So on the read side, there is actually these read lock and read unlock calls. Those do almost nothing. The only little thing they do is set a flag that says, or RCU read lock sets a flag that says, if a timer interrupt happens, please don't context switch because I'm in the middle of a RCU critical section. So that's all it really does is set a flag that prohibits timer interrupt context switches. The interrupt may still happen, but it won't context switch. And then read unlock unsets that flag. Or really, it's a counter of nested RCU critical sections. So these two functions are extremely fast and do almost nothing. And then this loop would sort of scan down our list. This is the call that inserts the memory barrier. So what RCU, this really boils down to just a couple of instructions. It just reads, it grabs a copy of this pointer from memory, issues a memory barrier, and then returns that pointer. And then we can look at the content and go on to the next list element. So the reader's quite simple. The writer's a little more involved. Writers still, the RCU doesn't help writers avoid interfering with each other, so writers still have to have some way of making sure only one writer modifies the list at a time. In this case, I'm just imagining we're going to use ordinary spin locks, so the writer acquires the lock. If we're replacing the first list element, we need to save a copy at the beginning because we're going to need to eventually free it. So we save this copy of the old list element, and now this code plays that trick I talked again about allocating a complete new list element to hold the sort of updated content. So we're going to allocate a new list element. We're going to set its content. We're going to set the next pointer to the next pointer in the old first list element as we're replacing it. And then this RCU assign pointer issues a memory barrier so that all these writes happened, and then sets the pointer pointed to by this first argument to be equal to that. So basically, this just issues a memory barrier and then sets head equal to E. And now we can release the lock. We still have a pointer to the old first list element called synchronize RCU to make sure every CPU that could have grabbed a pointer to the old list element before we did the committing write has yielded the CPU and therefore given up its pointer to RCU protected data. And now we can free the old list element. Any questions? All right. RCU, one thing to note about this is that while in the reader, while we're allowed to look at this list element inside the loop here, one thing we're not allowed to do is return the list element. So for example, using RCU, we couldn't write a list lookup function that returned either the list element or a pointer into data held in the list element, like a string that was embedded in the list element. Because then we would no longer be in control. You know, it has to be the case that we don't look at RCU protected data outside this RCU critical section, or we don't do a context switch. If we just write a generic function that returns a list element, then for all we know, the caller, I mean, you know, maybe we can persuade the caller to follow some rules too, but for all we know, the caller may context switch, or we'd run into trouble. Either we call RCU read unlock before returning the list element, which is illegal because now a timer interrupt could force a switch, or we don't call RCU read unlock. So the use of RCU sort of does put some additional constraints on readers that wouldn't have existed before.
A question about that?
Yes.
So are you saying in particular that if we had some form of like read element at index I method, that there's no way to structure this so that it could return the value held by the node at element I?
It could return a copy. So what would work, you know, if E_X is a string, we could return a copy of this string, and that's fine. What would be a violation of the RCU rules is if we returned a pointer to this very string sitting inside, you know, or a point. It would be a mistake to return a pointer into somewhere into E. Like if the string is stored inside the list element, we better not return a pointer to that string, because then it'll be, we have to not context switch while we're holding a pointer into RCU protected data. And the convention is, you just use that data within this critical section. And so it would almost certainly be breaking the convention, or this setup would have to be much more complicated if we ended up returning pointers into the protected data.
Thank you.
So I just want to sort of return briefly to the performance story. It's hard to characterize sort of what the performance is. I mean, in a sense, let's see, the overall performance story is that if you use RCU, reads are extremely fast. They just proceed at whatever. They have sort of no overhead above the ordinary overhead of looking at that data. So if your list is 1 billion elements long, yeah, reading the list will take a long time, but it's not because of synchronization. It's just because you're doing a lot of work for readers. So you can almost view RCU as having 0 overhead for readers, and the exceptions are minor. RCU read lock, just a tiny amount of work to set this flag saying no context switches, and RCU dereference issues a memory barrier, which actually might slow you down by a few dozen cycles, but it's much cheaper than a lock. The performance story for writers is much sadder. You had to do all the stuff you always had to do using locks. In fact, you have to acquire and release locks in the writer. And you have this potentially extremely expensive or time-consuming called the synchronize RCU. In fact, you can give up, internally synchronize RCU gives up the CPU, so it doesn't spin necessarily, but it may require a lot of elapsed time waiting for every other core to context switch. So depending on the mix of reads and writes and how much work was being done inside the read critical section, the performance increase varies tremendously from much, much faster if these critical sections were short and there's few writes, to perhaps even slower if writes are very common. And so when people apply RCU to kernel stuff, you absolutely have to do performance tests against a bunch of workloads in order to figure out whether using RCU is a win for you, because it's so dependent on the workload.
I have a maybe a tangential question, but we've seen that, I guess, when there's multiple cores being used, there's some added complexity to our usual implementations. And it's often these atomic instructions kind of come to the rescue. And that's assuming there's one shared memory system. But I wonder, like, what happens if a machine is trying to maintain like multiple RAM systems? How does it unify those?
The ordinary, well, at the level we're talking about, the machine has one RAM system. Okay, yeah, it's for all those sort of ordinary computers you would buy that have multiple cores, you can pretty much program them as if there were just one RAM system shared among all the cores. That's the logical model the hardware provides you. At a physical level, it's not like that often. There's plenty of machines out there that have this physical arrangement. We have a CPU chip. So here's one CPU chip, maybe with lots of cores on it, right? And you can get CPU chips with, I don't know how many cores these days, 32 cores, say. Let's say you want to build a 64-core machine, you can only buy 32-core chips. Well, you can make a board that has 2 sockets for chips on it. So now we have 2 chips. The fastest way to get at memory is to have the memory more or less as directly attached to the CPU chip as possible. So what you would do is you'd have like a very fat set of wires here to right next to the chip, a bunch of RAM. So it has direct access. And of course, this chip's going to want its own RAM also, right? So this is, I'm just drawing a picture of what you would see if you opened up a PC with 2 processor chips in it, RAM. But now we're faced with a problem of what happens if a software over on this chip uses a memory location that's actually stored in this RAM. So in fact, there's also a interconnect between these 2 chips, generally an extremely fast interconnect, like gigabytes per second. And the chips are smart enough to know that certain physical memory locations are in this bank of RAM, and other physical locations, physical memory addresses, are in this bank of RAM. And if software here uses a physical address that's over in this one, the chip is clever enough to send a message. It's basically a little network. Send a message over to this chip telling it, look, I need to read some RAM, please do it. And it'll go read its RAM and send the result back. You can buy 4 chip arrangements with the same thing with a complex interconnect like this. So there's a huge amount of engineering going on in order to map the straightforward shared RAM model onto what's sort of feasible to build with high performance in real life and fit in 2 or 3 dimensions. Does that answer your question?
Yeah, that provides a lot of context. Thank you.
Yeah. Okay. Right. And any questions on the actual technique? All right. So as I'm sure you've gotten the sense, of RCU is not universally applicable. You can't just take every situation in which you're using spin locks and getting bad parallel performance and convert it to RCU and get better performance, because the main reason is it completely doesn't help writes, makes them slower. It really only helps performance if the reads outnumber the writes considerably. It has this restriction that you can't hold pointers to protect the data across sleep, which just makes some kind of code quite awkward. If you actually need to sleep, you may then need to re-look up whatever it is, to do another RCU critical section after the sleep completes in order to look again for the data that you originally were looking at, assuming it still even exists. So that just makes code a bit more complicated. The data structures, the most straightforward way to apply it is the data structures that have a structure that's amenable to single committing writes for updates. You can't modify things in place, so you have to replace stuff. And so lists and trees, but not more complex data structures. The paper mentions some more complicated ways like sequence locks to be able to update stuff in place, despite readers that aren't using locks, but they're good to more complicated, and the situations under which they actually improve performance are more restricted. Another subtle problem is that readers can see stale data without any obvious bound on how long they can see the stale data for. Because if some reader gets a pointer to an RCU protected object just before a writer replaces it, the reader may still hold on to that data for quite a long time, at least on the scale of modern computer instructions. And a lot of the time, this turns out not to matter much, but the paper mentions some situations which I actually don't really understand, in which people expect writes to actually take effect after the write completes, and therefore in which readers seeing stale data is a bit of a surprise. You may also, as a separate topic, wonder what happens if you have write-heavy data. Like RCU is all about read-heavy data, but that's just one of many situations you might care about for getting parallel performance. You also care about write-heavy data. Actually, in the extremes, in some extreme cases of write-heavy data, you can do quite well. There's no technique I know of for write-heavy data that's quite as universally applicable as RCU. But there are still ideas for coping with data that's mostly written. So the most powerful idea is to restructure your data, restructure the data structure so it's not shared. And sometimes you can do that. Sometimes the sharing is just completely gratuitous, and you can get rid of it once you realize it's a problem. But it's also often the case that that while you do sometimes need to have shared data, that the common case doesn't require different cores to write the same data, even though they need to write some of the data a lot. And so you've actually seen that in the labs. In the locking lab, in the KLOC part of the lab, you restructured the free list so that each core has a dedicated free list, thus converting a write-heavy data structure, the free list, into one that was sort of semi-private per core. So most of the times cores just have to, don't conflict with other cores because they have their own private free list. And the only time you have to look at other free lists is if your free list runs out. So there's actually many examples of this way of dealing with write-heavy data in the kernel. The allocator in Linux is like this. Linux is scheduling lists. There's a sort of separate set of threads for each core that the scheduler looks at most of the time. And cores only have to look at each other's scheduling lists if they run out of work to do. Another example is statistics counters. If you're counting something and the counts change a lot, but they're rarely read, that is, the counts are truly dominated by writes and not reads, you can restructure your counter so that each core has a separate counter. And so each core just modifies its own counter when it needs to change the count. And if you want to read something, then you have to go out and lock and read all the per core counters. So that's a technique to make writes very fast because the writers just modify the local per core counter, but the reads are now very slow. And again, but if your counters are write heavy, as statistic counters often are, that could be a big win, shifting the work now to the reads. So the point is there are techniques, even though we didn't talk about them much, there are also sometimes techniques that help for write-intensive workloads. To wrap up, the RCU, the stuff we read about in the paper, is actually a giant success story for Linux. It's used all over Linux to get at all kinds of different data, because it just turns out that read mostly data, read intensive data is extremely common, like cached file blocks, for example, are mostly read. So a technique that speeds up only reads is really very widely applicable. And RCU is particularly magic. There's lots of other interesting concurrency techniques, synchronization techniques, RCU is magic because it completely eliminates locking and writing for the readers. And so that's just like a big breakthrough compared to things like read-write locks, which were the previous state of the art. And the key idea that really makes it work is the sort of garbage collection, like deferring of freeze for the what they call the grace period until all the readers are guaranteed to be finished using the data. So you can, as well as a synchronization technique, it's actually fair to view it as a very much so as a kind of specialized garbage collection technique. And that is all I have to say. So I'm happy to take questions.
Oh, sorry. Can you explain the stale data for readers? So I don't understand how that can happen, because you read in your critical section and you just get whatever data is there at that point, and then you just leave. Yeah.
It actually usually is not a problem. But the reason why it ever might come up, well, ordinarily, you know, if you have code that says x equals 1, and then you know, print done, gosh, it's pretty surprising if after this point, someone reading the data sees that value before you set it to 1. Right? That's maybe a bit of a surprise, right? Well, there's a sense in which RCU allows that to happen, right? If this is really, you know, if what we're really talking about is, you know, list, replace, whatever, you know, find the element that has 1 in it and change it to 2 with you know, using RCU, right? And after that finishes and we print, oh yeah, we're done. If there's some reader that was looking at the list, right? They may have, you know, just gotten to the list element that held 1 that we replaced with 2, and then a good deal longer, you know, and then they do the actual read of the list element. You know, they look at whatever the content is in the list element after we've done this. You know, they're reading the list element only at this point later in time, and they see the old value. And so if you're not prepared for this, so this is like a little bit odd now. I mean, they may even do a memory barrier, right? I mean, it's not a memory barrier issue. It's just like, and indeed, most of the time it doesn't matter.
I see. So this is when this replace is very close. So like the read somehow like starts before the replace, but it just takes a while. And
yes, yeah. If the reader is slower than the writer or something. Now, you know, I think this mostly doesn't matter because after all, the reader and the writer were acting concurrently, and you know, if 2 things happen concurrently, usually you would never have imagined that you could have been guaranteed much about the exact order if the 2 operations were invoked concurrently.
I see.
The paper claims, I mean, the paper has an example in which they said it matters. It turned out to cause a real problem, although I don't really understand why that was.
I see. This makes sense. And my other question was, it's called RCU because of idea 1. Is that right?
Read, copy, update. Yes, I believe it's because of idea 1. That is that instead of modifying things in place, you make a copy and you sort of update the copy, not the real thing.
Right. This makes sense. Thank you so much.
Yes.
So at the beginning of lecture, or towards the beginning, we talked about the O of n squared runtime for the cache coherence protocols for updating the read-write locks. Isn't this also a problem with spin locks where? Yeah. Okay. So like, what is the reason why we didn't discuss that aspect?
Why we didn't?
Yeah, or like, is there a reason that still exists, or like, what do spin locks do to address that?
Nothing.
Oh, okay.
Spin locks are hideously expensive if they're, or standard spin locks like XV6 has are extremely fast if the lock is not particularly contended,
Okay.
and terribly slow if lots of cores try to get the same lock at the same time.
Gotcha. Okay.
Yeah, this is one of the things that makes life interesting. And there's, I mean, there's locks that have better scaling, but worse. That have better high load performance, but worse low load performance.
Okay.
But I'm not aware of a lock that is. Anyway, it's hard. It's hard to get this stuff right. It's hard to get good performance in these machines. Other questions?
This might be unrelated, but can there ever be like lockings between multiple different systems, like not just for like not just contained to one system, maybe like multiple servers, perhaps?
There are absolutely distributed systems in which there's a sort of locking, in which the sort of universe of locks spans multiple machines. One place this comes up is in distributed databases, where the data, you split your data over multiple servers. But if you want to have a transaction that uses data that's different pieces of the data on different servers, you're going to need to collect locks that you need to basically collect locks from multiple servers. Another place it comes up, although there's been a number of systems that are essentially try to mimic shared memory across independent machines. Where the machines, if I use some memory that's in your machine, then there's some infrastructure stuff that causes my machine to talk to your machine and ask for the memory. And then the game is usually to run existing parallel programs on a cluster of workstations instead of on a big multi-core machine, hoping that's going to be cheaper. And something needs to be done about spin locks there, or whatever locking you're going to use. And so people have invented various ways to make the locking work out well in that case too, using techniques that are not, often not quite the same as this. Although the pressure to avoid the pressure to avoid costs is even higher in that case. Yeah. Anything else?
Thank you.
You're welcome.